Off the coast of the Faroe Islands right now, there is a 28-ton machine flying loops through the ocean on the end of a leash, and it is quietly keeping the lights on in roughly 1,000 homes, using a current that engineers had written off for decades as too weak to bother with. The machine is called the Dragon 12, built by a Swedish company named Minesto that started life as a spin-off from the aerospace giant Saab. And the reason it works where every other tidal machine has failed comes down to one trick. Instead of sitting in the current and letting the water push past it, this thing flies through the water, and flying through it means it moves several times faster than the current itself ever does, which is exactly what turns a weak flow into a strong one. That single idea just handed the tidal industry access to coastline it had given up on entirely. And it comes with something solar panels and wind turbines will never be able to offer you, a forecast you can trust years ahead of time. So in this one, we're going to follow the path from a slow drift of seawater to actual electricity on a grid, figure out what that electricity really costs per kilowatt hour, and then get into the harder, less settled questions, whether this hardware can survive years in the ocean, and what it means for the animals living in it. Start with the problem. Every grid running on solar and wind eventually hits. The power shows up whenever the weather feels like delivering it, not whenever the grid actually needs it. So operators are stuck holding expensive backup capacity on standby for the exact moment a cloud rolls over a solar farm or the wind just stops. And the deeper you lean into renewables, the more expensive and complicated that backup problem gets. Tidal power sidesteps this completely, because tides aren't weather. They're gravity. The moon and the sun pulling on the ocean on a schedule so fixed you can calculate the exact flow at a specific site decades before it happens. Of all the renewable sources on the table, tidal might be the only one you can actually plan a grid around instead of just reacting to. So why hasn't it taken over already? Because it's always been a speed problem. A traditional tidal turbine is really just an underwater version of a windmill, bolted straight to the seafloor, and the power a turbine like that can pull out of the water scales with the cube of the current speed. Push the current twice as fast, and you don't get double the power, you get 8 times as much, which means these turbines only make financial sense in genuinely violent water, current running above about 5.5 miles an hour, and water that fast is rare. It's a short list of narrow channels and straits scattered around the planet, and most of them are already claimed. The much larger stretches of ordinary coastal current, moving at something like walking pace, were never fast enough to justify the steel and the cost of harvesting them. That's the wall tidal power has been stuck behind this whole time. Minesto's way around that wall came from a strange direction. The company got started in 2007 out of Saab, where an engineer working on turbine concepts noticed something about water that most people miss, which is that it's almost 1,000 times denser than air. That density means even a slow-moving current is carrying a surprising amount of energy, far more concentrated than it looks from the surface. And if that's true, you don't need to wait for the water to move fast. You could fly a wing through it, the same way a stunt kite carves through wind, and generate your own speed instead of waiting for nature to supply it. That's the entire concept behind the Dragon 12. It's a wing roughly 39 feet across and 28 tons all in, tied to the seabed with a single cable, with a turbine and generator slung underneath it. As the tide flows past, the wing produces lift just like an aircraft wing does moving through air, and an onboard control system flies it in a continuous figure-8 pattern, sweeping it back and forth across the current instead of letting it drift with it. And here's where the physics gets interesting, because it's cutting crosswise through the water rather than just sitting still in it. The wing ends up moving through the water far faster than the current is actually flowing. Minesto claims up to 8 times faster. And since the power available jumps sharply with speed, a turbine flying through water at 8 times the ambient current can generate power completely out of proportion to how weak that current actually is. The kite is manufacturing fast water out of slow water, essentially building its own conditions to exploit. That's how something as small as an 11.5-foot turbine ends up doing work you'd normally need something much bigger to accomplish. The whole rig anchors to a single drilled foundation rather than a massive concrete block, keeping the footprint on the seabed small and the installation simple, and the power runs up the tether along a seabed cable and onto shore. The wing flies, the turbine spins, and current too weak for anything else becomes usable grid power. In February of 2024, in the Vestmannaeyjum Channel in the Faroe Islands, a Dragon 12 pushed its first 1.2 megawatts onto the national grid, enough to run around 1,000 homes, and made history in the process as the first tidal kite of this scale to ever deliver power to a real grid, rather than a test rig. Line it up against a conventional seabed turbine, and the difference is mostly about weight and where it can actually go. A bolted-down turbine needs heavy structure and needs genuinely fast water, which restricts it to a handful of extreme sites worldwide. A kite generates its own speed, so it opens up the much larger share of coastline where the current is merely ordinary. Minesto itself estimates this approach could more than double the amount of tidal energy worth pursuing globally. Other companies in this space, like Orbital Marine Power with its floating O2 platform, are still tied to those rare fast water locations, which shuts out most of the world's coastlines by default. A Dragon 12 weighs about 28 tons and actually breaks down small enough to ship inside a standard shipping container. You can install it with one modest workboat and a seabed anchor, no giant jack-up vessel required, no enormous foundation poured, and that lightness translates directly into cost, because less steel and a simpler install both mean cheaper electricity. The fairer comparison, though, is against offshore wind, since that's the option most coastal grids already reach for. One Dragon 12 produces roughly a third of what a single large offshore wind turbine puts out, so on raw output per unit, wind still wins outright. But raw output was never really the pitch here. The pitch is that you know exactly when the power is coming, and that it works in water no wind turbine could ever be planted in. On price, Minesto is projecting a levelized cost around $108 per megawatt hour once it hits 100 megawatts installed, dropping toward $54 as it scales further, and for full commercial arrays the target sits around 6 to 8 cents per kilowatt hour. That's still higher than the cheapest solar and wind available today, but it lands right in the range of offshore wind, which the U.S. Department of Energy priced at roughly $89 per megawatt hour back in 2022. The timing here matters more than the raw price tag suggests, because predictable power is becoming worth more every year, not less. The more solar and wind a grid stacks up, the more expensive it gets to smooth out their swings, paying for spinning reserves, backup gas plants, and increasingly banks of batteries just to paper over the gaps. There are already stretches where solar and wind flood the grid simultaneously and prices go negative, meaning operators are literally paying someone to take power they can't use. A source running on a fixed, known schedule avoids a huge chunk of that mess, and that saving almost never shows up when people compare renewables on a simple price per unit basis. Tidal flow also tends to peak at different hours than the midday solar surge, so instead of piling onto power the grid already has too much of, it can fill in the gaps around it. There's a geographic case here too, and it's a strong one. Remote islands and isolated coastal towns often have no cable connecting them to a larger grid, so they're stuck burning imported diesel at a steep price. The Faroe Islands are the textbook example, and they've already committed to running on 100% renewable power by 2030. For a place like that, a predictable local source tuned to their own fierce tidal channels is worth a lot more than the raw cents per kilowatt-hour figure would suggest, and the scale on offer is genuinely large. The U.S. Department of Energy estimates that fully developed tidal power could supply something like 21 million American homes, which is exactly why money and attention keep circling back to a technology that spent decades stuck in prototype purgatory. None of that means the kite is finished proving itself. The first limitation is just geography. This only works where there's a real coastal current to fly through, so inland grids, calm coastlines, and most of the world's landlocked population get nothing from it directly. Tidal is going to be a strong regional player, not a universal replacement. The tougher problem is the ocean itself, which has wrecked plenty of hardware before this. One earlier tidal turbine deployed in the Bay of Fundy had all 12 of his blades ripped off in just 20 days by currents stronger than anyone had designed for. Salt water corrodes metal, marine growth clogs moving parts, and constant flexing wears down every joint and bearing over time. The kite is lighter and simpler than a bolted-down turbine, and its tether takes less punishment than a floating wind platform would, but it's still a machine flying thousands of loops underwater, and moving parts are always the ones that break first. What actually settles this question is years of operating data, not one good season. Maintenance, at least, looks manageable so far. Minesto pulls the kite out with a single small workboat, disconnecting it from its seabed foundation remotely, with no divers and no underwater robots needed. And the company says a full launch or recovery takes under 2 hours. The first unit has already logged months of grid-connected running and come back for servicing without drama, which is a promising start, but it's a long way from a multi-decade track record. Then there's marine life, which is usually the first objection regulators raise. A machine spinning in a channel where seals feed, fish migrate, and birds dive looks, on paper, like an obvious hazard, and that fear alone has stalled tidal permits for years across the industry. The encouraging news came out of a US study in early 2026 that tracked more than 1,000 interactions between sea animals and a small tidal turbine and recorded 0 collisions with seals or seabirds, along with a 98% safety rate for fish, with seals actively steering clear of the moving blades. That study used a stationary turbine, not a flying kite, so it doesn't directly tell us how animals will react to something swooping through the water in figure eights, which is its own question that will need its own monitoring. But it's the best evidence so far that marine animals can detect and avoid these machines, and it opens a real path through what has been a serious regulatory bottleneck. From here, the roadmap is about turning one kite into a fleet. Minesto's next move in the Faroe Islands is the Hestfjord Dragon Farm, a first-of-its-kind array of 6 upgraded Dragon 12 units totaling 10 megawatts. Beyond that, the company has mapped out a 200 megawatt build-out spread across 7 sites in the islands, enough to cover around 40% of Faroe's electricity demand for an estimated 400 million euros. And the engineering keeps improving in the water itself. In 2025, Minesto found that simply lengthening the tether boosted the kite's power output by about 25%, which feeds straight back into making the larger farms more economical. Every month it stays in the water is teaching the company how to pull more out of the same wing, and Minesto is already eyeing other powerful currents around the world, including the Gulf Stream off the United States, where a steadier flow could push both output and cost in the right direction. For decades, tidal power carried a reputation as the renewable that was always 5 years away and never quite arrived, held hostage by the fact that only a small number of violently fast channels were worth the investment. What Minesto actually changed wasn't the ocean, it was the speed requirement itself, by flying through slow water instead of waiting for fast water to show up. And that quietly hands the whole technology a coastline to work with that's several times larger than what it had before. There are still real hurdles ahead. It only works at the coast. The ocean is brutal on hardware, and both the long-term reliability and the wildlife questions need years more data before anyone can call them settled. But there's a megawatt-scale kite feeding real power onto a real grid right now, a clear path toward full commercial arrays and a form of power the moon makes. Dependable in a way no cloud bank or calm afternoon ever could. If you want to keep tabs on the technologies quietly reshaping how we power our homes, stick around, because we'll keep tracking this one as it moves from a single prototype in the Faroe Islands toward the actual grid.